Hello, welcome to my presentation on observations of cleavage initiation in ferritic steels. My name's Mike Ford and I'm a PhD student at the University of Manchester and also employed by Jacobs. I'll discuss the goal of this work, a little bit about the background, the experimental programme, some post-test observations, some analysis based on these observations and some conclusions. The goal is to improve our understanding of the underlying mechanisms of cleavage fracture. This is generally assumed to follow a process with 3 steps in it. First, a particle fails. The particles are generally considered to be elastic brittle particles, typically carbides, and as the surrounding matrix plastically deformed, these particles fail due to plastic overload. And failure is generally assumed to be the particle cracks into 2, leaving a sharp crack. Then microcracks nucleates from this point. The sharp crack within the particle passes through the particle matrix interface, and now you have a sharp crack in the material, which can then propagate. Propagation is generally assumed to follow a Griffiths-like process, dependent upon the particle size and the critical stress. And then use this improved understanding of the above to support the development of local approach models, where local approach to cleavage models try to predict the probability of cleavage based upon the stress and strain fields at a given point in a material. And this improving the models would support their use to assess structural integrity of RPVs. There's limited experimental data on particle failure and microcrack nucleation available in the literature. We know that particle breaking is linked to plasticity from work by Gerland, who showed a linear relationship between the percentage of particles broken and plastic strain, up to strains of about 30%. It's worth noting that these were performed using specimens loaded in uniaxial tension. This creates quite different stress fields to those ahead of a crack tip. Also ahead of a crack tip, the plastic strains can reach 200%, so far greater than the 30% shown here. We also know that microcrack nucleation is linked to plasticity and temperature from work by McMahon. Here on the left we have the number of microcracks per 10,000 grains on this axis for different temperatures. These numbers show the plastic strain achieved in the test. What you can see is at low temperatures below -140 there's a roughly linear relationship between plastic strain and the number of microcracks. However, at higher temperatures, even at much higher levels of plastic strain, there are fewer microcracks. This is reflected in the plot on the right of number of microcracks versus percent elongation. The -140 and -180 data points follow the same pattern, which is clearly different to the -90 data points, where above 4% elongation the number of microcracks doesn't really increase. We also know from other work by Hoch that cleavage initiation typically occurs within 200 microns of the crack tip. As I said above, the stress fields here are quite different to those in a tensile specimen. Now, local approach models typically have simple assumptions. They either assume that all microcracks nucleate at the onset of plasticity, such as in Berremin model, or there's a gradual creation of microcracks, more in line with what Gerland showed in the Bourdet model, or there's sometimes heuristics which have limited experimental support, such as in the JFJ model, where nucleation is linked to the energy density in the strain in the plane normal to the maximum principal stress. So these are really quite simple and the experimental data is quite limited, but we think it should be a more complex phenomena, including things like the Laudet parameter or triaxiality possibly. We want to capture the full stress field and the effect of the full stress field, not just maximum principal stress or plastic strain. Therefore, a small experimental program was designed to try to examine particles and microcracks in stress fields similar to those ahead of a crack tip. A tensile specimen was designed with a highly constrained region in the centre and manufactured from A533B specimens. These were tested from -140 to -65 degrees Celsius, around the transition temperature of -109. The specimens were loaded in displacement control and examined destructively post-test on an SEM using slices along the notch. FEA was performed in parallel to try to predict the stress fields acting on particles and microcracks based on their location. Shown on the left is one of these specimens, and shown on the right is the FEA. So the tests were pulled in uniaxial tension with 2 clip gauges on either side to measure the displacement at these points. These could then be used to calibrate the FE model to compare the displacement across these points. The examination was performed in this region, with slices being removed to gradually move towards the centre of the specimen. So any particles or microcracks examined here could be measured and the position correlated to the closest element in the FE to obtain the stress and strain fields. Some example images are shown on this slide. What we see here is the normal metal matrix of the material. This point is a particle. At the top and bottom of the particle, the black regions are where the particle has decohered from the matrix, so a small void has formed here, no loads being exchanged, but the particle is still attached around this point. Above the particle appears to be a void in what was initially believed to be a region of highly strained material, but we'll come on to that later. Note that the particles in this material are quite large. The scale is 20 microns here. For a more modern, cleaner material, a large particle will be about a micron in size. The particle that's cracked internally is shown in image B, with two cracks, one there and one there. In image D, what appears to be a void in the centre, surrounded by lots of small cracks in this highly distorted region. And we can see image C here. We've got a better image of that on the next. Here we have a better view of subfigure C from the previous slide, and we can see at the centres an intact particle with no apparent internal cracking, which has decohered from the surrounding matrix. But in doing so, it appears to have created a field or a cloud of many sharp crack tips. So I'll trace around the outer edge. So note that this is far, far larger than the parent particle and appears to have a preferential direction, but there are still crack tips, or what appear to be crack tips, going out in many different directions. As a point of interest, some larger particles were also found in this material. If you look at the scales, some of these particles are up to or beyond 100 microns in length, and they've shown some very complex behaviour. The particle on the top right has many horizontal internal cracks, and at the same time has decohered from several points. The particle at the bottom left is cracked at several points as well, with decoherence and what appears to be these microcrack cloud fields around them, one in the centre, one at the top and one at the bottom, all of which are separate from one another. We focused the analysis on the smaller particles with a radius of below about 3 microns, as they seem more relevant and to modern steels and a little bit simpler to analyse. For the analysis, the small particles were split into two groups: parents, which nucleated a microcrack, and childless, which hadn't nucleated a microcrack. And then we looked at whether they cracked, decohered, or either of these events occurred. Only about 36% of parents actually cracked internally, whereas 47% of childless particles had cracked. So it was more common for childless particles to have cracked than parents, which wasn't expected. 99% of the parents had decohered from the matrix, so almost all of them, and 90% of the childless particles had. But all of the small parents had cracked or decohered. It's also worth noting that we only got one look at each particle in the slices on the SEM. This is just a simple 2D slice of a 3D structure, so it's entirely possible that that one particle, that one parent that apparently didn't decohere, had decohered in a different plane. I just couldn't see it. Cleavage failure was assumed to start with the particle cracking internally, which may then pass through the particle matrix interface to form a penny-shaped sharp microcrack within the surrounding material that's a similar size to the parent particle, which can then propagate depending on some kind of critical stress criteria. And the goal of this work was to better predict when will nucleation occur. But the work's actually shown a different process. A particle decoheres from the matrix. Cracking isn't essential; if anything, it limits nucleation. The matrix is then almost instantly overloaded. The particles themselves are elastic brittle particles surrounded by a matrix that at high levels of strain is almost perfectly plastic. So they have far higher strain energies and are bearing a significant fraction of the stress. So if they decohere from the matrix and shed all of that load, then the surrounding matrix appears to shatter to form a cloud with many crack tips, and the volume of the cloud is much larger than that of the parent. We didn't observe any microcrack propagation because we still assume a weakest link sort of event, where if a single microcrack starts to propagate, it will probably carry on propagating and fail the specimen, so there can only be one in a specimen. So we both want to understand when will nucleation occur and what will the size of the cloud be, because that affects the critical stress required to propagate from it. To try to answer the second of those two questions, here we've compared the cloud volume to the energy within the parent particle, where the energy within the parent particle has been obtained from multiplying the strain energy density at that point in the FE and the measured particle volume. Unfortunately, we don't know exactly when the particles nucleated, so all of these strain energy densities are calculated at the end of the FE simulation at the point the test terminated, not necessarily when the particle failed and the microcrack cloud nucleated. These figures split the data by temperature. If we assume that the lower energy values occurred closer to the point of nucleation, so are more accurate, then we can draw these lower bound lines, which are linear fits. It's a log-log graph, hence the curve. So this gives us a prediction of the energy at nucleation, and therefore the energy that created a given cloud. Putting the data back on the same plot again, we can see that the -140 and -125 lines are very similar, pretty much the same when you consider the scatter within the data, and both clearly different to the -85 line, which is 2 orders of magnitude higher. Note that this outlying point wasn't included because it's about 1.5 to 2 orders of magnitude lower than the other data points at -140. This data compares quite nicely to McMahon's data, where he showed the fraction of microcracks were very similar for -140 and -180, which were both much higher for the same percent elongation than the -90 data. Now we have the lower bound, what we'd like to do is shift the energies calculated at the end of the test to the lower bound line to give a prediction of the energy at nucleation. As I said before, the energy is taken as the strain energy density multiplied by the parent particle volume. The parent particle volume is fixed and measured, so we can't change that, so we need to change the energy density. Where the energy density in this case has been taken as this equation, which is the strain energy density in the plane acting normal to the maximum principal stress. This plot shows two figures, or two sets of data. First, these are the energy densities measured in the FE at the end of the test, and this is the line if we reduce the energy densities to shift the energies to the lower bound energy line. This gives us a nice pattern where the critical energy density decreases with the parent particle volume size, so larger particles are more likely to nucleate cracks first. These figures show the energy density for each temperature now, where the energy density is again reduced to the critical energy density, and the critical energy density decreases with particle volume. We now have the critical energy density for the three different temperatures. Note again the similarity between -140 and -125, and we can draw a best fit curve using a simple power law. To come back to the two questions from before, nucleation occurred when the strain energy density exceeded a critical value, which depended upon the parent particle volume and varied with temperature, and the size of the resulting microcrack cloud depended upon the energy released at nucleation and also varied with temperature. Local approach models typically treat the cleavage initiator population as a calibration parameter, such as in the Berriman model by varying m, or assume it's the same as the particle population, such as in the JFJ model. Using it as a calibration parameter poses problems for transferring the calibration between different geometry sets, so has its problems, and assuming it's the same as the particle population has been shown to be wrong here, where the microcrack clouds are much larger than the parent particles. But we can use these results now to calculate the population of initiators. In conclusion, the cleavage process in an A533B steel was observed and was not as expected. In this case, it appeared that the critical event was particle decoherence from the matrix, not particle cracking, as was expected. This leads to matrix overloading, which then shatters to form a cloud with many crack tips, and the size of the cloud is much larger than that of the particle. Microcracks may then propagate from the sharp tips within the clouds. A relationship between the energy within a particle at nucleation and the volume of the resulting cloud has been proposed, and this relationship has been used to derive a critical energy density for nucleation and the volume of the cloud created from a given parent particle. Future work aims to use the relationships above in an improved local approach model. And here are some references. Thank you for listening.